Hey folks, we're going to get started here with our Voyager talk, Habana-based AI machine for machine learning, artificial intelligence, Supermicro Habana Arista partnership. Okay, I'm going to get started, folks. I'd like to introduce the MC of this panel, Amit Majumdar. He's the PI for the Voyager system and the division director for the Data-Enabled Scientific Computing Group at SDSC. Take it away, Amit.
Thanks, Sean. Sean is the deputy director of SDSC and also the project manager of the Voyager machine. He did architected and worked on the machine, bring it to production, all those things. So yeah, welcome again. I have Darren Thomason from Arista and Steve Thorne from Havana Labs and Max Chang from Supermicro. And so I will go over some Voyager slides pretty fast, because we have the experts from Arista, Havana, and Supermicro. They can give their talk on the expertise, and then we will have a little bit of time for questions if anyone may have. So Voyager is NSF Category 2 award, where you can propose innovative architecture, and we are very glad to propose Havana's Gaudi training and Havana's first generation inference processors, and we have multiple co-PIs and a big team from SDSC that worked on the Havana project, bringing the Voyager machine to SDSC for the community. So again, Voyager is a very different architecture compared to the production HPC Category 1 machines. There have been other awards during to other HPC centers. So we are all in it together to bring innovative architectures to the community. And given its innovative architecture, we have a deep engagement with the research community. We want to work one-on-one with the community and explore these new innovative architectures for AI in science and engineering. So the Voyager project, given its innovative architecture, the first 3 years, we will work one-on-one with select research groups that we will kind of jointly figure out what the science, and we already have a lot of them. Even when we're writing the proposals, we presented their science case in the proposals. And in the last 2 years, it will be allocated just like any other NSF machines. Again, I'll talk about some of the innovative resource, but we have experts from Havana and from Arista and Supermicro to go further. And so right now, there are specialized Gaudi training processors and Havana's first generation inference processors. So it's a very AI focused hardware. It's not a general purpose machine. Deep learning frameworks or TensorFlow and PyTorch, as well as custom coding can be done on the Havana and the first generation inference processor. We have a lot of plan for engaging the community, doing workshops and user forums and sharing the experience with the community and engaging the industry in this process. I already mentioned, the first 3 years is the test bed phase where we work one-on-one, have a deep engagement with research team. We get a lot of support from AI experts at Havana in that effort to work one-on-one with users. And the last 2 years will be allocation phase. Without going too much into the details, but we have 42 Intel Havana Gaudi training nodes, each with 8 training processors, a total of 336 Gaudi training cards. And we hope to scale applications. We are already doing that. We have scaled benchmarks to 256 and higher Gaudi cards. And then we have 2 have an inference node, each with 8 inference processors. We have regular x86 and the Arista switch we have from Arista, of course, and storage is initially starting with Ceph file system, but given its innovative architecture, we may explore other parallel file systems. So training nodes for Supermicro. Again, we have the Supermicro expert Max here, so I'm not going to spend too much time here. You can see the specs. It has, it says the 6 400 gigabyte scale out connections. That's the innovative part of scaling out through the Arista switch. And then Gaudi architecture, it has 8 tensor processing cores and a general matrix math engine and 32 gigabyte of high bandwidth memory. Again, Steve is here, he can talk about it. And obviously the innovative part of the network is 100 gigabit Ethernet for scaling out for training. And then we have first generation inference nodes from Supermicro. you can look at the specs, and Max can talk more if there are questions. And then we have the first generation inference architecture. It also has 8 TPCs and 16 gigabyte of DDR4 and a large shared memory for inference. And these are the regular compute nodes that we have from Supermicro. And so Voyager has 3 distinct networks. Obviously, the 4 gigabit Ethernet for scaling out from each of the Gaudi nodes. So we can scale out to all 332 of them across the 42 nodes we have. And then we have the 20-feet gigabit bonded network for IO. And then we have a network for IPMI and other traffic. So again, we have the ICE expert here, so I'm not going to spend too much time other than pointing out that among the 8 Gaudi cards, 7 of the 100 gigabit Rocky connection goes to the other 7. So that's all-to-all connection, and the other 3, when you do it over the 8, is 2400 gigabit Rocky for scaling out to other nodes through the Arista 7808 switch. This is giving further technical details of basically what I just said. So the topology with 6 QSFP-DD scale out from each of the nodes. And here you can see the big picture of how the Arista switch is used to scaling out across all the nodes we have on the Voyager machine. Again, this is basically saying the 400 connections from each Gaudi node through the switch, non-blocking switch. This is showing the network connection for the IO to the parallel file system, which we are starting out with Ceph. And yeah, here they have 3 storage hierarchy: the node local NVMe that we have on the regular compute node and the Gaudi node, and home file system and the Ceph parallel file system that we will start out initially. But given its innovative architecture, we may explore other file systems. So as I mentioned, the ultimate goal of this project is trying out science and engineering AI applications on this innovative AI-focused hardware. And we listed some of the applications, from application domain and the AI techniques they are using, and the machine learning frameworks, and primarily focusing on PyTorch and TensorFlow, but Havana also has custom software that users can write with C APIs if they're interested. And there are many more applications and scientists that we're working with. Many of these are already ported and running and doing scaling applications. So our early user experience on this machine has been great. And as I mentioned, a lot of applications are in TensorFlow and PyTorch, so they do very minimal code change, sometimes few lines. And in some other cases, if some operators needs to be identified and not available in Havana, we work with Havana experts. And that's one thing I want to stress, that both Supermicro and Havana experts have been very supportive, very collaborative. We continue to work with the Havana AI experts as we bring in new science use cases to thoroughly analyze their applications, operators, and the models. And this is a Kubernetes-based machine, so that's a new experience for some of the SDSC, including myself. So that's great. We're learning new things. And there are multi-node training options, both with TensorFlow and PyTorch. And we have been doing a lot of training for the community and the interested users, and those are available through YouTube video. Again, this is a community project, means in the sense we want to energize the AI community to explore this new. So we have documentation and we have planned for user forums, and Havana has excellent documentation on reference models and how to use Gaudis and inference processors, as well as which models are already available on Gaudi and which models are coming next. Havana has excellent documentation. So the Voyager has been in the test bed phase since May 2022, which means we are engaging with select research groups to explore this excellent resource for exploring AI in science and engineering. And there are users even running with Jupyter notebooks. And obviously we have many dimensions to explore, given the training focused and inference focused hardware, the Rocky interconnect, the Arista switch, Kubernetes, Safe, Converge IO, which will allow GUI-based management of data science applications. And again, I want to stress the collaboration and support from Supermicro, and continuing work with Havana experts is vital for this project. And we are learning a lot of new things, given it's a new innovative architecture, and we want to work on it jointly with the community, share it with the community, engage the academic, national labs, industry. And so if you're interested in the Voyager machine, please send the email to consult@sdsc.edu. In that way, we can manage everything through a ticketing system, and we capture everything at the back end. So I will next let Max Chung, Staff Solutions Manager, Supermicro.
Hello. Thank you, Amit. Hello, everybody. My name is Max Chung. I'm a Staff Solutions Manager at Supermicro. Today, I'm going to share about some of the challenges we face and we overcame while building a Voyager cluster. So this is the process we use with 5 stages of rack integration process. We follow this to build a Voyager cluster as well. So this is from the first phase we design, then we do the assembly and configuration. They're all good, pretty smooth. The only thing it took us more time, that would be the design phase, because at the time we were deciding if we were going to use Arista pizza boxes, 24 of them to build a spine and leaf fabric for this application, or we want to use the big modular switch 70OA. And later on we decided, okay, we'll just use the big one because it'll be easy for us to troubleshoot. And actually we did need that to later on stage, because when we do the testing, we did encounter very serious issues on the whole cluster design. I'll share more about this. So first challenge we faced at the time was AOC, active optic cable. At the time, we were using the active optic cable to do home run from all the 2 nodes of a Havana system to the rack 5, the 5th rack, which we are using that to host 70OA Arista modular switch. And at the time when we were doing the initial testing, for 400 gig applications, there are 8 lanes in a 400 gig connection. It's actually 4 lane pairs. Each lane is running at 50 gig. So we have 8 lanes. There's a total 400 gig. And then the issue we found at the time, there was lane pair 1 and 3 will come up, and lane 2 and 4 would stay down for reasons we do not understand. So at the time we spent time to investigate, we try other solutions. Direct attached copper would work, no problem. Some of the AECs from other vendors would work, no problem. But this specific AOC, we try it and switch to switch, no. And then switch to other 400 gig NIC card, it will also work. But it just doesn't work when we paired it up with our Habana. No, at the time we were baffled, wondering why it didn't come up. And then we pull in resources from Arista to try to figure out how they made the AOC. And then we later found out there's a limitation on the AOC because they are using 2 clock signals from lane 1 and then lane 3. And then lane 2 depends on lane 1 signal, lane 4 depends on lane 3 signal. And then because the Habana system unique design, the scale out ports will be coming out of 4, actually all 8 Gaudi cards. Each port, each Gaudi card will contribute to one of the scale out port to aggregate to the 6 400 gig port in the front. So basically, we need 4 lanes running at different clock domain. They need to have that requirement there. But then the AOC at the time, it didn't meet that requirement. So I work with my team and Arisa and other vendors to come up with 4 solutions here. The first one will wait for the updated version of AOC, provide 4 independent clock domains, which will support our Habana application. Or the second one, they will use transceivers. This is the later one we identify as a winner because Arisa will support it. So this is a huge win here for our application. And then the third solution, we use AEC plus DR4 because we were considering the cost. AEC would be much cheaper than the transceivers. And the solution 4 will use all AECs. But later on, we decided we will use transceiver DR4 transceiver to replace all AOCs, and we were able to move on to the next phase. All right, so I think Sean will remember at the time before we about to deliver, we run into this issue. When we run ResNet 50 on multi-node, the workload will fail from time to time on different combinations of a node. We have a multi-node. When we run it like in single node, there's no problem because we didn't exercise the scale out port. But then later on, we found out if we use more than one node, then the workload will fail from time to time. And then at the time, it was difficult to troubleshoot. So I remember there's 1 week, I pull in all the engineering resources from my team, the hardware engineering team, and also from Habana Systems, and also from Arista to identify why there's a link will fail. Link, the whole workload will abort, and this is the issue. So at the time, I remember I invited our senior VP of the hardware engineering team to my daily sync up on the status of the progress we are making. At the time, we identify that there are multiple issues. Okay, so the first one is the BIOS. We need to address the initialization, Gaudi card initialization fail issue. So this is on our side. So I know our hardware engineering team, hello, they were super hard. And we at the time we established 2 CI/CD pipeline. So usually it will be our RD lab to verify the BIOS first, and then BIOS will come to us and put into our Habana system and run. And at the time, because the stress, the urgency, so we are running 2 CI/CD pipeline in parallel. So whenever we got a new BIOS build, they have a new parameter tuned in, the RD lab will run their test and our team will run our test as well. And then we feedback every day to the engineering team for them to try to come up with a solution to address the issue. And the second issue we address, we identify it was a few Gaudi cards when we during the stressful workload, one of the links would drop, would do the link flapping, and when that happens, the workload will be abandoned. We count it as a failed. So at the time, we were spending a lot of time to trying to identify which Gaudi card has the issue, and then we finally we came up with a systematic way to address this, to find out, to identify the Gaudi card that has this like a weak link issue. And then also thanks to Habana Labs support, now they put this into their production facility to do the QA. So they were able to identify what's not really up to our expectation, meet the spec, all right? Yeah, I think that's pretty much it. Then we overcome everything and we were able to deliver the Voyager cluster to SDSC. It was such a great honor to work with top scientists on this cluster at this scale, at this complexity. I have learned a lot, and it's also for our engineering team to learn a lot to deal with the complex project like this. All right, thank you.
Thanks, Max. Yeah, I'll request Max, Darren, and Steve to please come to the podium, and we can take questions from anyone. But maybe first Steve, and then Darren, if you want to talk about.
Thank you.
Yeah.
So at Habana, we are super grateful for the opportunity to collaborate with the San Diego supercomputer, with Supermicro and with Arista on an innovative deployment where the value of integrated networking is really brought to bear. Habana's engineers ourselves are using this cluster to test out all sorts of new ways of deploying large scale models. We're running things like GPT-2 already at scale and taking full advantage of the Arista switch, the Supermicro system, so that we can use deep speed and all sorts of innovative ways to scale out. And so this is just the beginning of a long and fruitful partnership. Thanks for having us here with you.
Sure. So I'm Darren Thomason, and as well. We were really excited on what we could do with SDSU and with regards to the Habana cluster. For us, networking, we just don't want to delay everything, right? So one of the things we found out with the AI workloads is that so many times we're waiting on the network. And I think with the way that you guys have designed this and built this out, and the deep buffers for the Arista 7800, we can keep the network from holding up the workloads. So that's really our goal in life, is to make things work more efficiently. Obviously with 400 gigs, soon to be 800 gig on that same chassis. So if you guys decide to go down that path in the future of 800 gig, we can run it on that chassis the same way. We also have bigger chassis too. So if you need some of those, we could probably figure that out. Although it's going to take a year to get them, but that's a whole different story. But we're excited about it and look forward to the solution as it continues to scale out.
Thanks. See, anything else you want to add, Max? No. Okay. Yeah, maybe I have a question for Steve. So Steve, what kind of applications you are from your company side you are seeing on the Gaudi, and then there are future generations of Gaudi that are already out, right? And what kind of models you are preparing and optimizing on the Gaudis?
That's a great question. So we chose to start with the most popular kinds of AI models in computer vision and natural language processing. We've posted to our library over 50 models already that we've optimized that can run on Voyager already today. The goal that we have is to make it frictionless. So people that have already done development work on, let's say, a GPU architecture can migrate over to Voyager with maybe just 1 or 2 lines of code change. The domains include compute vision, like object detection and segmentation, natural language processing, and now really the forefront is large language models. These very large foundational language models are going to take advantage of the capabilities in Voyager to be able to run things like stable diffusion models, GPT class language models. And this is where a lot of our energy is spent today, is running those models. And now also not only doing the training regime, but the inference regime on the same systems. So we have a demo in our booth in 1838. We encourage you to come by. We're running on Gaudi a diffusion model where you can do the text prompts and have images generated on the fly based on whatever inputs you give to it. That's one of the fun ones. But you can imagine that there's applications for that in the real world where people are going to be doing multimodal language, video, and picture searches and generation. And so we're glad to partner with San Diego Supercomputer at the forefront of these kinds of advances in the industry.
Thank you. We'll see if any question from audience.
So I have a question for Steve. Where do you see the large data? Where do you see the training on large data samples? Which areas that you've encountered have the largest training sets?
Oh, well, there's, as you know, Frank, there's a lot of data that's sitting out there that commercial organizations are collecting. A lot of it has to relate to their customer service and engagement on recording conversations through the customer service lines. But here's the other biggie. You go to a country like India, they've got 22 or so different local languages. These large data sets now are being harnessed so that they can translate on the fly across all 22 languages from any one to another. I mean, I see there's all kinds of just language translation applications alone that have data and can harness that data in ways that have not been done until now.
So I guess that's why all these language models are, and scaling them up and inferencing on them is a big part of the
Exactly.
commercial AI and yeah.
And in years past, when it came time to do inference and deployment at scale, people wanted to use very lightweight, low power inference kinds of cards at the edge. But these very large language models now are requiring more compute resource. And that's why we've migrated our software set so that even on the same hardware that like Voyager is deployed, you can do a training regime and then also do the inference regime right on there. These GPT class models require that kind of compute capacity just to spit out the inferencing.
So you're moving away from, let me make sure that I understood. You're moving away from separate hardware for inference and training to doing the inference, the large scale inference on the same hardware as the training?
Yeah, and we're not moving away. The industry appetite is growing so large for these big data sets that the compute infrastructure needed to run some of the inference is increasing. We still offer the low power inference dedicated option like the Goya cards that San Diego Supercomputer have deployed. We do see there's applications for those like in cashierless checkout, where you need a lightweight inference right there at the scan out, or let's say in the vehicle. But for some of the very large data sets, it requires data center capacity.
So I'm asking in part because that's sort of coming up. We just at UCSD, the Data Science Institute just hired a new faculty who's talking about petabyte scale inference.
Yes.
And so I'm supposed to help them figure out where to do that and how to do that.
Voyager would be a great opportunity
There we
to
go.
test it out.
There we go.
Yeah. We want to make sure that you're
Yes.
you get access to all the codes as we release them such that you can do those.
Basically, he's starting next spring. He's going to show up and be a faculty member, and he wants petabyte scale inference. And we're going to have to figure out how to do that.
Okay, let's talk to Sean and Amit and make it happen.
These new faculties are very demanding, right? They show up and want to do petascale inference. Yeah.
Yeah.
And the data isn't at UCSD, it's somewhere else.
Ah.
So put one in first.
So this question's for the SDSC leadership with all the team. So we're a big believer in how you serve the long tail of science. Which of the AI enabled or optimized and accelerated workflows do you see making it into the long tail space? Maybe even through the portals or anything else that you do, and about what's the path to that like?
I'll give some answer from what I know, Frank and others. I mean, Ilka here, she's doing a lot of AI applications with Wildfire. So Voyager, the user applications we had, they span all domain sciences, from high energy physics or someone doing cardiac image analysis, even the radiation oncology department at UCSD, they want to apply AI, and actually they are literally running on Voyager now, their application, which is very clinical, application where they want to make a preliminary guess on what kind of intervention to use for some kind of cancer. So that's an example. A lot of weather modeling and climate researchers are also using deep learning, to get to where they want to get to, like weather forecasting, but without doing the very rigorous mathematical solution which they do on supercomputers to forecast weather. But can they use data science and deep learning to get where to get that, and use some of the parameters they use in even mathematical modeling? They have to make some they have to cut corners because they don't have that kind of compute power. So can the deep learning get them where they want to go, but using less data science approach, less computable? So we see from all kind of areas we are seeing. I think these things are all pretty well established. Obviously there is still more research need, and then as their requirement goes to meet the time deadline, then that's when to scale out, right? That's one thing we want to explore on Voyager with the scale out network. And I think Ilka has a lot of AI applications.
So I would answer your question by saying that it's all resource constrained, meaning in the AI in lots of other spaces outside AI, outside machine learning, it is actually science constrained, that you don't need more for the things that you want to do. When I look around in machine learning today, people do things at small scale because they don't have access to big scale. And I believe that if you gave, the moment we give access and more resources are available that are easy to use, you will have an explosion of everything. And why do I say this? Is when I'm a founding faculty of the Data Science Institute at UC San Diego, and data science today is synonymous with AI ML, basically. It's a synonym. And when I look around, my faculty colleagues who develop technique, who develop algorithms, who are sort of doing stuff in various, in all kinds of domains, invariably, they restrict themselves arbitrarily to what they can do and not what they would want to do. And so I believe that the moment we make it easier to access larger resources, you'll see an explosion of the 99% on larger resources. And this is very specific and to the IML space, much more so than any other thing that I've seen.
Yeah, this is it. Thank you all. We'll be around. Appreciate it. Probably should.
Check, check, check. Hey, folks, come on over to SDSC's booth. You'd like to hear Ilkay Tintas talk about convergence and composability. This is the marriage of software, hardware, science for the public good. This is a tremendous project she's working on. I should say projects she's working on. And come on over. There's more pastries, more coffee, but more importantly, Ilkay is going to give you a dynamite talk right now.
Hi, everyone. I'm Ilkay Altintaş, and I'm here to talk about convergence research at SDSC. And as you've seen in our booth, we are here to grow a versatile computing ecosystem. What does this mean? It means big data, computational science, data science, computing at any scale, and also its applications. Let's talk about a little bit of the applications. What are these applications in our time? The first thing about applications they are complex. They have a lot of complexity in them. And that's a sign of our society where we are at. We have the biggest challenges of our time to solve, starting with climate change, to economy, to pandemics, and the effects of all of those at the societal scale. But these are too difficult to solve alone. We need to learn to collaborate, and we need to learn to use our systems effectively in service of these collaborations. At the NSF level, this became a program that's called Convergence Research, and SDSC fully embraced this program. What does convergence research mean? It means putting together the best of our expertise in a cross-disciplinary way. So going from disciplinary, multidisciplinary, interdisciplinary work and translating that into a societal context. So the product of convergence research is impact in the societal scale. SDSC's Cyber Infrastructure and Convergence Research Division, CI-Core division, is built around this concept. Traditionally, we are the division of SDSC that builds cyber infrastructure projects and in a multidisciplinary, interdisciplinary way. And our strength lies in machine learning and cyber infrastructure and putting those together with the best of data management and computing platforms. So now what we are doing is we are actually combining that with social sciences and our partnerships at the societal scale to add it to our scientific and educational portfolio, these projects that we actually work with our stakeholders to impact their area of work. So this is a new way of doing things. And we are creating a culture around this and in this new way of doing things. And I'll show you a few of those projects that have been societally impactful in a significant way. And for all these couple examples, we have many more that has different significant impact levels of their own. So maybe we learned a lot from the COVID-19 pandemic. We actually learned that the problem isn't solvable when the problem happens. You need to prepare for it. And during COVID, we had data coming from disease models, virus models, wearables, public health records. Many data sources happened without a commons platform for those data sources to actually be integratable. And on the other hand, there were a lot of work going on without integration on spread modeling, on understanding the virus, the atomic interactions at the molecular scale of what the virus does, drug design, vaccine design, cure, you name it. And on top of these, the economic impact and mental impact and all kinds of secondary impacts of COVID are not even modeled at the moment. So we are not able to bring the data together to predict what will happen next. So when you think of these, if we were able to integrate these with the right stakeholder communities, we can do all kinds of things for decision support, policy making, even the integration of cure. One of these projects, actually, we are so proud that Ilya Zaslavsky's GeoAct team won one of the HPC Wire Response to Societal Plight Awards. So I think it's also really an ode to our impact in this area. They were able to use agent-based models to create prediction of the COVID spread in the society, and in particular in small communities of interaction like schools. But the team didn't stop there. They worked with the public health department in San Diego with the school system and created models of our schools, school buses, and things like that for us to be able to understand what happens when the schools are back in business with the students interacting with the school system. So this was used not just by the school system for decisions, but by parents, by the public as well, to understand what's going to happen to their kids, or should their kids go to school. So it has impacts in all levels of the society. And this is what we mean truly by convergence research. That last layer that makes what we do accessible to the society, to the people who will benefit from the products of research. The other COVID-19 project was TempPredict that I was personally involved. These rings that we are wearing, they actually are special. The Aura rings, we had a collaboration with Aura, the company, and we had 70,000 plus individuals donating their data to the study. And what this means is that data coming from that many sensors on a daily basis as a time series, that needs to go to a compliance system, that needs to be anonymized, that needs to be converted to a time series database, and that needs to be made AI ready so we can actually do models to generate alerts of the disease at the individual scale for 70,000 people. This requires 4 different data systems and the required composable computing platforms underneath so we can actually serve this system. So that alert then goes back to a doctor's office that combines it with daily surveys so that the patients can be alerted they might have COVID. And it was incredible that some of these alerts, that what we call asymptomatic, they were actually receiving alerts, taking tests, and they were positive. Because it wasn't just about temperature, it was about heart rate variation, how the person sleeps, how they actually react to certain things like activity during the day. So that's another example that made real impact on a short time span of 6 months, thanks to our researchers. The other one is in earthquake modeling. We work with the Southern California Earthquake Center for 2 decades, and our models get translated into visualizations to inform the public on what's coming, what's the next big thing. And Yifeng Cui won many awards, including Gordon Bell nominations and things like that. But the main thing here is we didn't just stay there. We actually worked with the right groups to communicate the results of the work. And my team in fire modeling also does significant societal integration projects and initial attack response. We were actually able to change the culture in Southern California on how California does initial attack through public-private partnerships, which turned into a $30 million governor's program in 5 years. So this is a significant success for computing, not just for SDSC, but everyone working in this. And we are doing similar things for prescribed fire optimization and the use of edge computing at the fire front by decision makers. And this all is, thank you. Thank you. This all builds on a commons platform that we are extending to other domains. So we are actually doing a lot of data and model commons work to fuel this type of ML and cyber infrastructure integrated, machine learning and cyber infrastructure integrated societal convergence projects. Open topography is another building block to something like the firework, because for 2 decades again, we've been maintaining a topography archive using LiDAR measurements. So we are the only open resource that thousands of people actually come and download topography data for their work. And when we talk about topography, we talk about everything under our feet. So anything that land cover becomes important. Fire research, for instance, we are using open topography to host and serve our LiDAR data sets for land cover about the trees, becomes important like anything that does something like that becomes a user of open topography, which directly is applicable at the societal scale again. So our work in that sense is creating these building blocks in data management, data science, advanced cyber infrastructure, and domain science, but it doesn't end there. They're very collaborative in nature, these projects, but then they go through a translational innovation and become part of the scientific, societal, educational landscape for impact. I think this is a model for supercomputing that was only made available at SDSC in this scale. And we are now embracing that as convergence research. That means not just translation of this into this, but it's bi-directional. We actually work with stakeholders to understand their needs and show them what can be done for them using cyber infrastructure, AI, machine learning, and also build products for them to drive our research. So in that sense, we are learning from our communities and communicating what we can do to them. So it becomes this truly collaborative, integrated solution picture. So systems that we are building, this versatile computing ecosystem, are then designed to embrace this collaborative team thinking. That's why SDSC is the first supercomputer, Expanse is the first supercomputer with composable systems made available as the part of the infrastructure. The second application context is we are in the age of big data and AI. What this means is AI happens here in the middle of things, and it integrates into modeling and simulation and other things that scientists work with. But it also has to embrace, and we need to bridge that integration of big data and IoT, just like the TemPredict system I showed, to make that solution happen. And that means we need to have a combination of capacity, which is the traditional supercomputing, with capabilities that make the rest of it work. AI integrated processing units, FPGAs, edge systems, big data management systems, and many more that are coming up in the IoT space. And big data and IoT and AI capabilities combined with capacity gives us our workflows that become the foundation of this convergence research societal impact picture I was painting a while ago. And there's a recent report from the National Academy of Science, Engineering, and Medicine on how many areas actually have this AI integrated science in it. And it gives us some glimpses of how others are doing embracing an AI. And that means another requirement for our systems, they should be capable of seamless integration of different systems. So we need to actually bring the AI systems together with other types of computing systems to serve workflows as capability services. So we need to think of it as an ecosystem that we integrate systems and services that are capable of doing specific things, the best in their area, but maybe integratable with other systems as well. Third context for applications. We are, because of just what I said, we are in the age of many systems. If you look at HPC Wire, some recent news, here's Dan Stanzioni and in TAG, the GigIO collaboration for composable systems. There's the Expanse, there's many four AI systems, including our Voyager funded by the National Science Foundation. There's some news of data fabric and open storage network, and many others that are PATH project that are funded by the National Science Foundation. This makes a very heterogeneous picture. And there's a reasons for it because our workflows are heterogeneous. Problems we are solving are data and AI integrated, heterogeneous, and they require these collaborations at the scale of the systems. And existing systems gives us some glimpses of what's needed and what can be served, just like data, continuum, high-speed connectivity. These are software defined now. They're actually programmable at all scales. And they run microservices on top of them for that programmable access. But the growing needs between these is interoperability, dynamic scalability, on-demand access to them, but at the same time in a way that we can measure and predict their performance, so we can compose them together, compose the right system for the right service at the right time. So this is not something we had traditionally in supercomputing, and now we are seeing many applications of that happening. So then we need to think, we still need to think capacity as a service, but we also need to think of things as a capability integration ecosystem. So strategically build services that are capable of doing things on our systems so they can be integrated into solutions. So this is the application ecosystem for convergence research that takes our, in essence, capabilities and integrates them into solutions at the societal scale at SDSC. So now I'm going to switch a little bit and think about why this integration matters at the technical scale. There are three things. One, dynamic composability, I talked about and said it really matters if you want to solve a problem through using a heterogeneous workflow. And also building systems and services, I said, through teamwork, through collaborations to integrate into workflows is important. And the third thing I said was we need to actually measure and predict their performance. But the other thing that we need to really be careful about is while we do that, how can we be responsible and ethical and private so that we don't make harm through AI, just like we've seen at the societal scale through some examples. So what this means is at the dynamic composability scale, we have the systems, just like part of Expanse, our national research platform, and many others. We have resource managers that can pool these resources into integratable bits as composable services. So if we get these three layers right, and there are different approaches to it, we have a dynamically composable system. On top of that, then how do we enable teams to create AI integrated workflows? Then using these services to integrate them in a way we can coordinate them. And these services could be a Jupyter notebook on a Jupyter Hub as well. As simple as that to a high scale, high capacity simulation run at the exascale. And all of these need to be integrated. We can't ignore data anymore. We need to have systems that are centered around data if we are talking about AI. So that was our second point of how you would create a reference architecture. And the third one, how do you make impact and make it responsible at the societal scale? And this is the blue part, is what I refer to as the convergence layer. How do you make sure you build the right use-inspired interfaces, build the right user experiences at the societal scale for science, education, and other scalable practice, using decision makers, policy makers, public, training and teaching personnel, and integrating it with team science practices, talking about reproducibility and making things reproducible and responsible. These are technical things. These are not anymore social things on the edges and the perimeters of what we are doing that we can ignore. When you put all this together, it becomes a complicated solution architecture. Let's simplify that a little bit. What this means is systems integrated in use-inspired solutions with compute storage network, data management, composition software and APIs, and services and applications on top of those. So we need to get these layers right if we really mean societal impact. And we need a lot of things improved, including data capacity in our computing systems that serves different needs. So some of our composable systems, Expanse is the first composable system that was funded by the National Science Foundation. Expanse has many innovative operations because the idea is we can enable more users, the longer tail, not just the long tail, but the society itself, like the integrating into everything we can. And how composable systems was implemented in Expanse is reserving some of the resource as a Kubernetes pool that can be federated with other Kubernetes pools. And there are a lot of things that we are learning and building as we go, how to, for instance, do that in a dynamic way, because it requires a lot of measurement infrastructure underneath and understanding how that federation can happen. But I'll be happy to talk to you more about those. And these two partitions and dynamic provisioning is what makes the secret sauce for Expanse, composable systems. And the specific research platform, which nicely evolved into a national scale research platform, NRP, is served by a Kubernetes pool called Nautilus. It's a cluster. So the first composable system with Expanse using many nodes, and this shows actually the power of it. This is from PRP from last year. Storage rotating through Ceph was 4,000 terabytes just at the petascale. And this shows how you can compose things and get actually petascale storage there. Installed CPUs and GPUs now at the thousands level since last year. So this is growing nicely. So what we've done with Expanse was using the Kubernetes part of Expanse and composing it with Nautilus. So we can start laying applications, so those capability integration services on top of them. What does that mean? That means you actually have a topology for composition using Admiralty. Admiralty is the federation software here, and it is at the computing scale. So data federation is another thing that we have to work on as a community. This requires a joint data fabric behind it. So what we also added, not just Kubernetes, but K3S, a lighter version of Kubernetes, to show composability of Expanse and Nautilus with an edge computing capability called Sage. Sage is an infrastructure that a number of us worked on over the last 5 years. And it is to install accelerators plus sensors, nodes that are called Waggles, into NSF's networks. And it starts by having the sensor side and a virtual Sage that we can actually train deployable AI models that could be used for inference at the edge in a multi-tenant way. So these are edge computing capability that multiple users can upload and run services or schedule to run services. So it requires a different scheduling capability. So what we were able to do is use Expanse, Nautilus, and Sage. So Nautilus is the Kubernetes, Expanse is Kubernetes, and Sage is K3S, which is the lighter weight Kubernetes, and pool them together so users can build models, train models on Expanse and Nautilus, and schedule the trained models as inference services on Sage. And in this case, our tests happen on a virtual Sage, and it was deployed a couple of times for testing services, but this capability is coming soon as a multi-tenant resource. And when you have a, this composable system, how do you actually make it available? Users can come in and they could actually schedule nodes that they'd like to use for their Jupyter notebook. And they could train and deploy through that Jupyter Hub platform. So another application of this in fire simulation, there are a couple of applications actually. When you think of fire response, what you want to do at the edge is continuously be on a camera and detecting smoke. When you detect smoke, locating that smoke is another part of that AI, but that should trigger a more capable resource to run a fire simulation, which is in the Wi-Fi project, something we've done. And at the same time, the smoke and that detection that you have becomes part of a different training workflow. So you're continuously training the model and deploying it at the same time that's running in real life or real time on a camera platform to detect the smoke. And that triggers a fire workflow on more capable Expanse and Nautilus. This happens also in another prescribed burn simulation, which actually integrates also cloud providers, because here we have a capability to integrate also with the cloud capabilities so that we can actually spill over to commercial clouds when needed. And at the time of need, or sometimes things are down, we can move out pretty fast. So that's also another advantage of the composability in this context. So these are a few examples that actually talks about there's a data layer to build these applications. There's a compute layer that's composable, and there's a user front-facing layer. So there are stacks emerging to generalize this concept. Just like my reference architecture, we are now putting together middleware and software behind those. So these are not the only applications, right? There's the neuroscience imaging applications. TempPredict that I mentioned actually use these composability features that I mentioned. But here, what we are talking about is heterogeneous workflows that need many resources, many types of data systems at once, so we can actually integrate them without too much work. You know, it still takes work. These are not cost. These are not turnkey applications and systems, but they are really complex if we don't provide the systems to the community with a doable amount of work to make those possible. So composability and systems serving that heterogeneity becomes really important in that level. And it's very complex. As I said, our problems are complex to solve. And we are looking for partners and collaborators at the societal scale, but also in computing space to develop these systems together, to build systems that bridge infrastructure to solutions. And please find me, or my email is available here. And if you're on the market, we are looking for people who can work on these exciting projects with us. Thank you. I don't know, I can take a couple of questions probably. Judy.
Thank you for a great talk. I think the composability is very interesting. Can you elaborate? Can you elaborate the composability? What is the current state? What is the pro and the cons?
So that's an excellent question. What is the pros and cons of composability? Composability, I think at the HPC level is still an experiment. Because when you think of Kubernetes, it's built for a unified namespace, not for high capacity applications. It's built for what it's doing. It's the integration of this pool of software. So I think our HPC community over time will come up with its own tools and with its own ways of doing composability because we are a lot more complex than a single namespace. That data federation is actually the biggest challenge right now, because when you have multiple applications running across these systems, how do you make sure you can serve those applications and serve their data system with their resource at the right place? So that's one cons of it, so to say. The other is, I think it's a culture shift. Our systems are built as black box systems. They're either available or not. You don't know much of the performance available. As a user, you don't have a lot of data. So when you're trying to build things on top of dynamic capabilities, those data systems right now that give us insight, a gray box insight, I call it, is not available. So it's hard to provision, predict work that, and we have, I don't see this as a cons. I think it's a challenge that we need to overcome. I don't see in that sense many cons going forward, because this is needed and we have to do it. If you call it composable systems or, capability systems, it doesn't matter what we call it, but this is something that's needed and we have to provide this capability. Otherwise, we'll only be able to serve a very thin slice of our user groups and lose on our impact. Thank you. Other questions? Thank you again. I think this is the end of my time. And we have a great set of talks coming up also the rest of today.
Hello? Oh, there we go. Hi, everyone. My name is Shava Smolin, and I'm one of the co-PIs for CloudBank. So CloudBank is a 5-year NSF pilot project designed to facilitate researcher access to public cloud resources. And it's a partnership between SDSC, UC San Diego, University of Washington, UC Berkeley, and Strategic Blue. And we will be co-presenting with our public cloud partners, AWS, Google Cloud, IBM Cloud, Microsoft Azure, and Oracle Cloud. So we're going to start with an overview of the CloudBank project given by myself and Kathy Yellick, one of our other co-PIs on the project. And then we'll give each of our public cloud partners a few minutes to speak about their platforms. And then we're happy to take questions from folks. So I wanted to start first with the motivation for why we created CloudBank. And so when we were working on the proposal, we reached out to our science researchers at our local institutes to find out what types of pain points they were encountering when trying to use public cloud resources. And there are 3 main challenges that people were running into that are illustrated by the quotes on this slide. The first was getting onboarded to the public clouds was difficult. Getting started with the public clouds, learning how to use the tools. And then the third area was billing and monitoring spend. So these are the 3 areas that we really focused on with CloudBank. So we went into production in August of 2020. And as you see, we currently support AWS, Google, IBM Cloud, Microsoft Azure, and we're expecting to support Oracle by early next year. This is our project website at cloudbank.org and a screenshot of our homepage that you'll see there. It has the 3 main services that we provide within CloudBank to address the pain points I mentioned on the previous slide. The first is our user portal. And so this is a place where PIs can come to learn about CloudBank and then learn about how to get access. And then if they get a CloudBank award, it will handle all of the account creation and the access to get researchers onboarded quickly and then help them track and monitor their spend. One important aspect of CloudBank is that it is designed to be multi-cloud. So once a researcher is on CloudBank, they can use any of the clouds that we support. And the funds do not leave CloudBank until the researcher spends. So this makes them very flexible. They can be used wherever they're best needed. Another important aspect is that we configure and leverage CI logon so that researchers can log into our portal as well as all of the cloud vendor portals using just their normal home institute credentials. So not creating additional accounts, just use the accounts they already have. The second service that we provide is our financial operations. So this is where all of the logistics and working with the cloud vendors happen. So paying the bills every month so that the researcher doesn't have to worry about that. They don't have to put down a credit card. They can just focus on the technical aspects of using the public clouds to best support their research. And then one of our partners, Strategic Blue, is a reseller, actually a cloud FinOps company in the UK, and they're an important part of our financial operations. And then the third service is our education and training. So this is our onboarding materials, getting started guides. We also provide some tools for facilitating running classes in the cloud that Kathy will talk about in a bit. And then we also have a help desk support. So a little bit more information about our support. We use a tiered model, which is available through help@cloudbank.org. And so when we get any messages into our system, we will take a look at the question. And then if we can handle it internally within our team, we will. But if there's like fine-grained questions that we need help with, we'll defer to the experts at our public cloud partners and then facilitate any interactions as needed. So we started with what we're calling the V1 funding model. And the way that that worked was that certain NSF solicitations were made CloudBank eligible. And you can see the list of the current solicitations that are still CloudBank eligible. And so if you were a PI that was submitting a proposal to one of these solicitations, you would use one of the cloud vendor calculators to estimate your cost, and then provide that cost estimate along with some justification into a supplementary document. And the estimate that you allocated for spend would be independent of the formal budget. And the reason for that is that the cloud spends would not go through the awardee institute. They would pass directly to us at CloudBank. And the advantage of that is that we would not charge any indirect costs on those funds. So that's one of the main benefits many PIs would see when using CloudBank is if you allocate 50K to spend in the cloud, that's what you get to spend. In May of this year, we introduced a V2 funding model that became available through a Dear Colleague letter. And so what this does is allow any PI with an active size award to request funds directly to us at CloudBank. And so there's a simple form on the website at cloudbank.org/request. And the PI just needs to put in some information about themselves, the award that they have, and then again, using one of the cloud vendor calculators, and then provide a few paragraphs of justification. We receive those requests, we review them internally and try to turn them around within 2 weeks' time. A few other avenues that we have to get access to CloudBank is through our discretionary community awards. And these are independent of NSF awards that you don't need to have a prior award to apply. And these tend to be smaller, but they can be used for exploratory purposes or also for teaching classes in the cloud. And then the fourth model we have is what we call the enterprise model. And this is designed more at the institute level where anybody who's interested in adopting CloudBank at their home institute or pieces of the CloudBank model at their home institute can reach out to us and then we'll work with you. And we're also looking, that could also apply at the award level as well. So if anyone's ever interested, please send us email at help@cloudbank.org. This is a sampling of some of the awards we're currently supporting on CloudBank. The first award that we supported was in the area of IoT and edge computing. And we have a few more awards in that smart and connected communities area. But the largest amount of awards we have are probably in machine learning. And there's some examples there. We have 7 awards in quantum computing, which became available through another Dear Colleague letter that was released earlier this year. We also have some awards that are related to data processing tool development. We have 1 award in chip design, which was pretty interesting, and then a few awards related to classroom training. And then we're also supporting a few awards outside of the SCI's directorate, particularly with the geosciences. And so you can see as well that we also support large universities as well as smaller MSI universities as well. So a few more statistics. Earlier this month, we passed a milestone of supporting over 100 NSF awards across all the different cloud providers. A number of them are multi-cloud. A large number of them do come from that V2 funding model that I mentioned earlier. And then we also have our discretionary awards, which can be used again for exploratory purposes. But a good amount of that money is also used for teaching classes in the cloud. And this comes from a tool that is developed by UC Berkeley called the Berkeley Data Stack. And so I'm going to hand off next to Kathy.
Thanks very much, Shava. So yeah, I'm going to talk a little bit about how we use CloudBank for teaching at Berkeley and with some of our partners. So just to kind of give you some background, we've developed different ways of teaching at Berkeley because of the scale of our undergraduate population. Many of you, if you're in computer science departments, you know that the huge increase in the number of undergraduates has really stressed all of our traditional ways of teaching. And in Berkeley, our introductory courses in both computer science and data science have over 1,000 students. So in fact, one of our instructors this year is teaching over 2,500 students this fall. So, you know, you have to do something different if you're going to teach that many students at once. They don't all fit into a lecture hall on campus. So it has to be, and they're doing programming assignments and things like that. So the curriculum is really based around this idea of interactive Jupyter notebooks. And so the students all they don't really know anything about CloudBank, to be honest. They just know they've got this Jupyter notebook. That's what that's where they come in through. And we've got over 10,000 students every month that are using these servers. One of the big classes, the introductory data science classes, is a fairly well-known class that we just called Data 8. There's 1,500 students in that one. And this is really, the cloud is absolutely essential to making this work. So just to give you an idea, if you're not familiar with Jupyter notebooks, this is what it looks like. If you're really not familiar with it, think like a very powerful sort of Google Doc where you can put text in there, but you can also put interactive code that you can click on and link it to data sets that then will run on the code and things like that. So you can imagine it's a very sort of constrained environment for the students that they can do their homework assignments in them, and they don't have to worry about installing software or anything like that. They can use it from any internet-enabled device. This was developed pre-pandemic, but I will say it was a huge asset that we used and have moved a lot of other courses over to taking advantage of it. It can also have interactive references, so you can have videos and things like that that are embedded within it. There's a project that CloudBank specifically supports with a nonprofit called 2I2C, which is a pilot project with community colleges. So because this introductory data science course has been so popular at Berkeley, we've also been exporting it to community colleges and other schools, both in the area and further afield, such as Howard University. So they use these managed services, and you can see the long list of schools there. So it's been, I think, a great way for us to try to also kind of advance the way people are thinking about things like data science or computer science throughout the different throughout the educational system. And we get a lot of our undergraduates through transfer programs that come from community colleges. So this is a really big help for us as well at Berkeley. I think with that, I will hand it over to Rick, who's going to talk about AWS.
Thank you. Clicker and a button. Good morning. I think it's still morning. Come on, you guys in the back, you want to sit down? They were very comfortable chairs, I'm telling you. No? Okay. Hi, I'm Rick Friedman. I'm trying to figure out how to work the buttons. There we go. Okay. Very happy to be part of the CloudBank program. Have been involved with it for a number of years, and really think the CloudBank offers a lot for the community that we all live in. From our perspective, we're very excited about how it enables researchers. Shaba was talking about that. You saw an example of how you can use CloudBank if you're new to this environment, if you're trying to understand how to take advantage of these cloud technologies. It's a great way to do it. One of the things she sort of slid over it a little bit, and I still think it's a big deal, is the utilization of your funds. CloudBank really gives you a whole different way of thinking about that model and how to take advantage of it. And that can really offer real benefits. And we have a number of people that are currently using the CloudBank environment. So I wanted to just touch on two things briefly. We were asked to talk a little bit about some of what we have. One thing I wanted to touch on is that, when we first started it, a lot of the focus was on what I would call classic research computing type workloads. But what we're finding, and I think you saw this in the workloads that are coming on, is more and more AI and ML work. And I think that that's very interesting. And one of the things CloudBank's great at is touching on the people who have no exposure to this stuff and bringing them in. We have a lot of people in portions of the research world that haven't used, they've never been off their laptop. This is a great way to move them forward. The other piece I wanted to highlight is that from an AWS perspective, there's a lot of different training options that exist out there. There's in our skill builder environment, there's a set of training. There's a series of 10-minute tutorials. And then I want to highlight, and by I know the way, I know exists for all the other people too. So this isn't just an AWS one. On the CloudBank site itself, there are specific learning paths on how to use particular vendors within the environment. And that's really, really helpful to people. All right. I could go into a lot more, and I'm known for doing that, but she said to try to keep it short, so I did that. Anybody who'd like to talk about this stuff or stuff in general, we're over there. Come visit me, grab me. All right. Did I meet my time limit? All right.
Thank you so much. All right. Perfect. Thank you so much, Rick. Rick just gave me some really good advice that a lot of the interesting stuff at the conference is at the periphery. So I'm going to do a quick walk around very soon. But thank you to Shava and the Cloud Bank team for having us here. Google Cloud is really proud to be partnering with Cloud Bank. Full disclosure, this is my first supercomputing conference, and I am so excited to see all of this. The number of different providers of scientific computing services and hardware, number of different researchers, faculty, students, is just such an exciting environment. And I'm glad that we as Google can play a relatively small role over here. What do I want to talk to you about today? Not too much. When I think about the journey of scientific computing on cloud, I think it's going through its phases. Phase one was, what are you talking about? Why do I need the cloud for scientific computing? And I think we are past that phase. Step two was, okay, it makes sense, but how do I pay for it? And it seems costly. And that is where I think programs like Cloud Bank, which are demystifying how the usage of cloud can be done in a cost-effective way, are really, really helpful. Now, step three, which is where I think where we are right now, is how do I get started, right? You have made the case that cloud is the platform that can support science. I, as a scientist, want to try that. Where do I get started? I don't want to become a cloud engineer. I don't want to become a cloud native network specialist, right? I just want a simple environment, a simple notebook where I can get in and start doing my science. So two things, if you take away from my talk today, one is RadLab and the other is HPC Toolkit. Both of these are open source, modular, blueprint-based platforms that we have created, through which we are hoping that more scientists, more researchers will build these templates, these blueprints, through which other students and researchers can start doing their research on the cloud. And this week itself is a very momentous week. We have supercomputing happening here where we have launched HPC Toolkit. And if you are interested and want to play around with it, do come to the Google Cloud booth. And at the Government Summit in DC, we launched the RadLab UI. RadLab is nothing but an open source platform. It's available on GitHub. It has pre-built modules and templates for different kinds of research workload, be that genomics, be that chip design, be that protein folding. And our hope is that more students and researchers will use these platforms and keep adding to these libraries and thereby share the goodness of science that they're doing. So yeah, so I'll end it at that. I'll not go into any of these slides, which have a lot of details. But if you want to do some hands-on work on any of these templates, these modules, we have labs set up at our Google Cloud booth. Please do come in and play around with this.
Thank you. Thank you. Thank you. Thank you, Astitwa. And thank you, Sawa and Cloud Bank team for giving us the opportunity to present here. So we are part of Cloud Bank since the beginning and supporting a lot of researchers in terms of research consulting to time of onboarding and kind of trying to answer the questions related to how to use cloud efficiently. So out here, it gives me opportunity to reach out to further audience and say, please reach out to us if you feel you need some help in using our cloud or any other cloud. So IBM Cloud in general, our motto is multi-cloud hybrid cloud company. And we are giving a lot of solutions where you can do research on different cloud using any platform. So I see a lot of time in the academic world, people are interested into a lot of GPUs, CPUs, and so what we call resources. Sometimes it becomes really heavy, intensive use case. And if you don't plan well, it can just blow your research budget. So that's where we help in doing those things in optimized way via our consultation and with the help of Cloud Bank too. So IBM HPC workload, last time I talked about our cloud solution and got a feedback like you guys should talk more about HPCs. So this time I put a slide about HPC. So you can make truly a hybrid HPC solution on IBM Cloud. Take your HPC solution, use our LSF solution to put it into either an IBM Cloud or go on to your enterprises if you need it. Now, what we have done, we have kind of mimic exactly same interfaces and created the same environment as your on-premise as well as on cloud. So try to leverage this solution. We already have team out here who can explain you more about this. Not only this, we have a lot of courses which are available for free for you to use in your classroom or for give it to your students. And there are cloud resources for free to use with those. And if you need additional resources through CloudBank or through us, you can get more resources for your research and teaching purposes. So with this, I'm happy to hand over to
Do we have Jesse? Okay, I didn't think I saw him. Okay, we're gonna move forward to Oracle, and we've got Santosh. Santosh Vas.
Good morning, good afternoon. First of all, I would like to thank Shava and their entire UCSD team for having us here. First of all, we are new to the Cloud Bank, but not new to the academic institutions. We've been there known as Oracle Academy for many, many years. And now with the Cloud Bank, our main goal is to basically help researchers overcome all the operational issues, because researchers should not worry about day in, day out, their mundane tasks. All they want, give us a platform and then we can start our research, because the timing is very important and crucial. That is where, we provide all the wide range of cloud capability in our cloud. Also, we are very proponent of, utilizing your own skills. So the skills which you have learned should not go waste basically. So you can see all the tools which are being very familiar to the developers community. We are leveraging those all tools into our cloud and basically enhancing or modernizing. So also the most important part is that all these research data is very crucial and sensitive. So obviously the researcher will worry about, oh, you are putting my data into the cloud, how safe it is. And that is a very genuine concern. And from very beginning, we put these security by design, not by choice. We just put it into our design. So any code we develop, security is built into there. And as you can see here, the security is from core to edge, all the way we have security built in. So researchers should not worry about, somebody is stealing their data, because data is encrypted at rest and at transit to begin with. Also, some of the offerings in the compute, everyone has these. However, where we little bit differ is with our GPUs. And recently, the collaboration with NVIDIA, we are, doing a lot of art of possible things now, particularly in the medical area and the research area. Storage, we have pretty much, wide range of storage available. Networking also, we have, end-to-end. I will go a little bit faster into this. HPC, another issue earlier with the researcher where, oh, HPC, those compute will cost a lot of money to us, but that's not true now. We have low cost, flexible, and high performance compute environment related to HPC and GPU are now available. So that way you don't have to worry about the costing. Also, we have something called universal credit, which means you will pay only what you use. That kind of model is there. Also, we are continuing expanding. Right now we have a 40, a data center all around the world. We are adding some more. And then with Azure, we have also interconnect to their data centers. Now, the most interesting part, which is new, is Oracle for Research. And, Cloud Bank is doing a tremendous amount of work to the researchers, helping them do research, which is, for the human cause, right? Now, with the Oracle Research, we are providing them, end-to-end solutions. We are working with them. We are giving them the white glove compartment, white glove service. It's not that we just give their cloud and gone. No, We are helping them in installing, and in be there in entire journey with them. Okay. Also, we have, based on our infrastructure, we have built a lot of technology, which is very helpful to the researchers. We also have AI and ML services, which now is become a core component of research activity. Also, a lot of analytics services, which is built into our Gen 2 infrastructure. So it's a very fast environment there. Also, we now have come up with the open data services. And in the open data services, researchers can share the data anywhere, where they are working. They can do the sharing, and that is available to us now. What are the use cases? Life science data set. A lot of these data sets are important to the researchers, and they want to share among their research community. So we have that life science data set, geospatial data sets, and machine learning data sets. So all of these data sets are available for researchers to make use of it, do a combined research there. Also, a lot of, the performance enhancement capability, you can see as HPC are benefiting a lot of research institutions because of the speed and, the core capability. Also, to help, research community, we are also offering award, Cloud Starter Award. So, we invite some research papers from the research community, and based on them, we do selection and provide the award to the, them researchers. Also, we have a project awards, for the researchers. And then we have 2 free trial options available, always free and free trial. These are the 2 free options available. You can just oracle.com cloud free, and you will have those environment available for you. And this never expires. You can use anytime. Some of the customer story, I've just put 1 or 2, but there are many of them. But this is a very interesting one, having virtual humans on OCI HPC. So entire human, body is, available on HPC for doing research. And a lot of these biotech companies are helping also there. Then pharmaceutical research, lot of research now are using our AI and ML technology. In fact, during COVID, a lot of these services came very handy. So basically at the end, they explore the world with us, our services. Thank you.
Thank you so much. Any questions from anyone? Rick has a question. No, he has a comment. All right. Yes.
Come on, you got to ask a question. You got 4 cloud vendors up here. It's your chance to abuse us. Come on, guys, get up here. Come on, stand here, be brave. Go ahead. I think I saw a hand go up in the back.
Yeah, it's me. I had a question. It's probably more for Kathy and Shiva. So one worry I've had about individual researchers swiping their own credit card in a cloud is that publicly funded data then becomes, in essence, dark data because it can't be reused or found. It seems like Cloud Bank may have a role in keeping that from happening. So, potentially in the future, how can you collate all the PI data or?
Yeah, so we specifically do not work with sensitive data at this point, just because it's very complicated. So we do simplify that by just not allowing PIs to put sensitive data at this point. But as far as, again, not putting down their personal credit cards and things like that, that's really where we hope to facilitate that researcher access.
Where do you envision the data going or staying after the research is done?
So we do have an offboarding process that we would go through with the researcher to find out, can the data stay there? Do they have other grants that will cover it? We would work essentially individually with each researcher to find out what's the best solution for them to going forward. If it means taking data off the cloud into somewhere else, then we can help facilitate that. Yeah.
Can I add something to that? Can I add something? While you're passing the mic, one of the things, it's not really an answer to your question, but it's related. One of the things that's great about CloudBank is if researchers use CloudBank, you as an institution, you can get reports on what your researchers are actually using versus if they run it on their own credit cards, you don't. So I know from all of us, I mean, we get reports from CloudBank and we can share that with all that. So at least you have a better visibility of what's happening out there.
So I was going to say the same thing, basically. I think that the starting premise is a little bit off. Research data is dark. It is dark today. And CloudBank provides a theoretical accounting mechanism, because if people use the cloud, you at least see what gets put in, what comes back out, and you therefore have a fighting chance at accounting for the dark research data. And that's the first step in any kind of curating, et cetera, et cetera, et cetera. So in a way, we're doing a tiny step forwards in a problem where we're starting off with basically the vast majority of research data is dark. Does that make sense? It's basically the same as you're saying.
Yeah, no, actually, yeah, that's a good point.
Yeah, so just to answer that question, one of the great idea is to take out all those operational things from you, right? All those accounting and all those credit card swapping, and less you focus on the research activity. That's all. That is the main purpose of the CloudBank.
I mean, I'll just add that I think there is a sort of national question in here of how, or even internationally, but how are we going to support long-lived data sets from science? And so I agree, this doesn't entirely solve the problem, but it at least gives us another mechanism besides things that are at other supercomputing centers for, places where the data could live in perpetuity.
In the interest, one second, in the interest of really spinning people up, because that's what we're here for. So how many of you can answer how to actually pay for saving the data? Because actually, no, that's one of the biggest challenges. And I think it behooves us as a community to also go back to the funding agencies. And one of the biggest pushbacks I get is it's an unfunded mandate. And I just bring that up so that we all acknowledge that's part of it and how we can help drive what happens there. So, sorry.
Yeah, so I've been trying to do cloud at Los Alamos for a long time. And the biggest issue is somebody could make a mistake and spend a bunch of money. So what I would like from the cloud vendors is this researcher gets 10K done and they're all like, but what about, continuity of operation, whatever. My continuity of operation is he spends the 10K and then it's done. And nobody has been able to give me a story that yes, you can subdivide it into accounts, give people a thing because it's too complicated or something. So that to me, I think is a big barrier to cloud usage at the labs in my opinion.
So I completely agree with you. I think this is a huge problem with using commercial clouds. I do think CloudBank takes us one step closer by monitoring the usage and sending you at least emails saying, hey, you're about to run out of time, you're out of time or whatever. So, and it doesn't ask you to give your lab's credit card, right? I mean, although the labs are, this is an NSF thing at this point, but I agree. I think that on the cloud provider side, we would really like to be able to just cut off access. And I think the other thing you brought up is being able to subdivide an account. So you're a PI and you've got a chunk.
Yes.
We know how useful that is. And I think that's something that we would have to, right now, I think it's not something you can sort of allocate to each graduate student, but that certainly would be, I think, possible within the framework.
Well, one of the ways, and I think it applies for all vendors, so someone can steal the mic from me and hit me if they want. First of all, you hit a sensitive topic because no. And the reason why is I do not want to be the person that goes to a researcher who's this far away from solving cancer and telling them we turned off their machine. So I leave that to you as their sysadmin to solve that problem. No. Right. No.
Yeah.
Right.
Yeah. So sorry. To take care of that problem, and that we heard those problems from many people. What we have done, we have created a dashboard, like accounting dashboard. We are a single pane of view. And what we have done there, we have put the threshold. Like if your account is reaching like 75%, you will be notified that you 75% is used, 25% is used. So all those kind of accounting management have been put into the dashboard itself. So that will take care of that problem.
Okay, but I have to say that, why is it that we can't get them shut off when we want them to be shut off? Like when they're out of allocation? Is that, I mean,
So-
certainly this is not a technological limitation.
It's more of a business limitation. As Rick said, we don't know where you are in your research, and if you shut down, probably it would be like the business commitment issues. No, not only profit. Like as a researcher, you might be doing amazing things, and we don't want to.
Yeah, and everybody came to and everybody put their drinks on your tab. One of the ways that I mean, I understand the challenge, and again, I think at some point there's tools within all the vendors to actually kill jobs. But that is, in fact, what I find most people do, though, the successful institutions create role-based controls. And so you go in and you basically say, okay, you're a PI, you can run whatever you want. You're a grad student, you can't run any more than 8 cores at a time. You're Rick, you can have 1 core for an hour a day because we don't trust you. And that seems to be a way to manage it. But this is, I don't know that there's an answer to this, because I'm talking to a group here. I can tell I'm talking to more of a sysadmin group. And when we go talk to the researchers, they're like, if you touch my job, I'll kill you. All right, I'm with you. All right.
I mean, I'll just add to that like what we are doing right now over here, hearing from all of you and getting this feedback, that helps us create those systems that will eventually solve this. I'm not saying that it's like our infrastructure or our stack itself is not capable of doing that, but there are other kinds of customers that we work with who would not like that. So now as we get deeper into academic research and we understand what the pain points and challenges are, we are building the dashboards, the systems, the kill switches that are needed.
Go see any of the booths, and I guarantee you someone can demo that for you.
As somebody who's now responsible for helping people fix the problem when they have a $10,000 charge on their credit card, I can tell you it's a huge problem in the universities. We have to get exception after exception to retroactively pay for something like that.
One of the things that CloudBank does offer, though, that's a big deal. You both touched on it a little bit, is the estimation of what you need. Okay, and there's 2 parts to that. There's what's the actual number, but then also researchers haven't really had to answer that question before, right? If you buy a box, I buy a box. And I don't know really what I need. Maybe I needed more, maybe I didn't, but I got a box, I'll run it on the box, right? And so one of the things, the tool suites that they have is the ability to do cost estimations, is the ability to actually rationalize your cost estimations. And encouraging your researchers to do that ahead of time makes a big difference.
In the spirit of controversy, I'll just say a lot of these people are HPC people who are used to estimating how much time they're going to get on an HPC system, which is very different than I'm going to go buy a piece of hardware and use whatever I want on that piece of hardware. So I think that is something. I mean, that's part of what we got with this version 2 of the funding model, CloudBank 2.0, is you have to estimate it up front, but you you don't have to put it in hard coded in your grant proposal when you're writing it.
And I think very soon different researchers or someone would come out a Terraform template or anything which says like, you put the money guarantee and we will just granularly, because almost all cloud provider now give you instant billing. So they can just write the Terraform provider and say, okay, you kill all the resources. And then you take the responsible for running that script. I think problem can be solved, but it's little controversial, as ma'am said.
Is there time for another question? Okay, this is more kind of popping up a level. You know, I'm just curious, how do you, and I came in a little late, so you may have talked to this a little bit, but how do you see CloudBank sort of fitting into the larger portfolio of resources that you have, be it whether it's IT, you know, local resources, the NSF or DOE resources, other national resources? So where do you kind of, what do you think the niche is here that this is helping to address? Did you catch that, Kathy?
I didn't hear it. So. Oh, CloudBank in the NSF portfolio. So you know, what's really interesting, I think, is right now it's mostly, right now, I think Bank is mostly for size researchers, but there's a lot of interest that we're seeing. I mean, I certainly get requests, and I think CloudBank too for researchers in, you know, material science and chemistry and so on. So right now, and that's why I think, as Shava said, that most of the projects that you've seen are there's a lot of machine learning. I mean, there's a bunch of other really interesting things, and there's these new quantum. But machine learning is probably the dominant, it's going to be, I'm sure, the dominant usage in terms of number of hours. And so I think that's how it fits in. And right now, NSF is funding, there's two models, but the current model that is popular is they gave CloudBank a chunk of funding to buy cloud credits, and now we're handing them out to researchers who have active size projects. And so they just write a little proposal in order to get time. So that's been extremely popular. You know, our version 1 model was when you write a size proposal, you had to estimate the amount of cloud you wanted, and you had to pay for it out of your own proposal budget. And that was, you might imagine, not quite so popular. Yeah. So I think you know,
free is more popular.
Free, right? So it's free, and it's sort of year at a time. What do you need? So it's interesting. We need to do a different experiment that splits those two and says, okay, well, what if we start charging you for it, but you pay as you go, which of course is one of the huge advantages of the cloud, is you pay as you go. And whereas the original NSF CloudBank model was pay up front, estimate what you need, and the money is gone.
Well, but it's not like there aren't systems in the NSF portfolio that are good for machine learning, right? So what do you think makes this uniquely better for some of these versus what's already there?
I mean, I think there are a number of other really interesting kinds of projects, some of which don't necessarily fit with HPC. There are people doing like networking studies, or people trying to measure the cloud. There are people doing a whole bunch of stuff like that, IoT kind of stuff. But then also, I think that this idea that you can get pretty quick access, it's like maybe you turn around to get access, that's very different than even probably an NSF center where you got to write a proposal and so on.
Okay.
Yeah, I mean, there's certainly overlap for sure, but there's also unique services that the public clouds provide that are different. Yeah.
Yeah, and another advantage is that you don't have to wait for the resources. Earlier, getting the HPC resources will take months and months. Here, you have easy accessibility through the CloudBank. That's it.
So let me risk getting myself into trouble to answer your question in a different way. I'm the director of the SDSC, Frankfurt Fund, and I see a different social expectation in the science community from the rest of the scientific community. And there is sort of almost split happening as far as I can tell. There's the people who are willing to wait and the people who are not willing to wait. And the people who are willing to wait is traditionally the HPC community. They grew up with batch systems. They've always used batch systems. They have everything they've done in their life is a batch systems. And those people are less likely to move to the cloud. And then there is the people who have never used an HPC system. They're coming from an environment where instant gratification is what they grew up with. They essentially are the ideal customers of the cloud. And that crowd happens to be the CS researchers that do machine learning. And it's very dominated socially by the expectation of what's the access time. And if you have an expectation of access time instantaneous, then you're a cloud user. If you have an expectation of access time, oh, I can batch this, then you're an HPC user.
I'm going to add one more thing to the access time, which I completely agree with. I mean, I remember a few years ago being at a meeting with a bunch of NSF computer science researchers who said, oh, we need a whole bunch of computing. Well, we have to go to the cloud. And it's like, well, that's not what the rest of NSF did when they needed a whole bunch of computing. But, you know, for them, that was just sort of the first way for them to think about it. But I do think resilience is another big issue that we've got to think about in HPC. And I mean, I do really think that we need to think about networking the HPC centers together so that jobs can move seamlessly between them when one is, you know, down for an upgrade or whatever.
Just to add to what you said, well, first of all, because I like to get the controversy going, I'm actually impressed. I'm known for my ability to insert large groups of people in one smooth statement, and I give you credit for that. No, I think it was a very legitimate point. And I think there is some truth to what you say. I would add another piece, though. I think that there are rules to getting onto the large systems. Okay, and did I break it? Uh-oh, I talked so long. We burned out the battery, guys. I don't know. But I think there's also what we're starting to see is people coming in and saying, I want to try my experiments on a smaller scale before I go ask for 1,000 cores over there or whatever it is. And I can cycle faster to figure out what I need. And so I think there is some truth between first the mindset of the people, but I think the other things that the cloud vendors bring is access to technology at a faster rate than those systems can build. So I think that's what we see bringing people in.
I was going to go back and answer Shane's question one other way, which is, as somebody now who's not running a supercomputing center is involved with Cloud Bank, I think ideally there would just be a sort of ecosystem in which you had certain kind of money that you could spend, or maybe it's credits and you could spend them on a commercial cloud and you decide, you know, what type of services you want, or you could spend them at a supercomputing center. And there would, you know, and maybe the supercomputing center would offer you much larger, you know, job sizes, or maybe they're cheaper because they're not going to give you the same kind of immediate access, right? So those are, and then it's just a free market system.
Actually, you got me to think about that. And I think there's a component that also, beyond just the sort of CSE explanation, there's also, I find that the community of people that want access to this kind of technology is much larger than it's been in the past. And they have a different understanding of how to take advantage of it. You know, batch systems are intimidating. And the cloud, and what Cloud Bank offers is a much simpler way to get into it. And I think we're seeing a lot of researchers doing that. Yeah. Oh, it's got one.
Yeah, I just say that, you know, another question for HPC centers is what do they do on-prem cloud? So a lot of people are saying, okay, great. So why don't we just do on-prem cloud, and then we could actually control the access to it in the way we have in the past. So it's not the case that you're going to be able to clearly go to cloud vendors unless they address the money issue. So I do think that's something you guys should be thinking about. Yeah. Just one other thing I just want to say to you, you know, at Atlanta, we have a quantum computing center. And I've offered, you know, that you get the latest and greatest quantum computing by going to Bracket or whatever, because those guys are putting it on. So the quantum vendors want to put it on cloud, and people want to access them through cloud. So that's definitely a winner. You know, you get access to more machines. And related to that, not directly an answer to your question, but I think some of the conversations we've had here are about, you know, the type of researcher and then what they're used to and then what kind of a system they want, and this versus that kind of an approach. But I think it's also a question of like, how can we do all of the above approach? And that is an area where I think that the cloud providers have a lot to learn from the supercomputing centers. The amount of investment, the way that supercomputing centers support the students and researchers through new kinds of applications and libraries and tools and data sets, that is something that we are also looking at, that how can we build that kind of an ecosystem that, depending on the kind of science it is, what kind of work a researcher needs to do, they go to the right platform that works for that kind of research. So I think eventually that is the goal. In some cases, you know, on-prem clusters will work. In some cases, cloud will be there, but it's an all of the above approach.
Hello. Yeah. Oh, good. On the other side, do we have to have a computer center to only support users on their own machines. So I agree, the user support is huge, but it's often very siloed. You only get the support to my system. What if I want to use more than one system? I'm afraid to talk to you because you will talk me into use something that only works for you. And when I go to the next system, I have to spend a lot of time optimizing for that. So as a user, I would rather have disaggregation, if you want, of user support and hardware providers, because as a user, I want to write once around everywhere if I can, and somebody who is dedicated for a certain system, it's too siloed.
Yes, we are seeing that, like in our hybrid cloud community, multi-cloud community, how can we give a platform which is not tying someone to a particular vendor, but using all the infrastructure as commodity, giving the researchers the unified view. Work is going on. A lot of hybrid cloud strategies are coming from different providers. Some are very specific, some are open. Even Berkeley started a program on the sky computing, which is kind of standardizing those interfaces. So we are seeing things are coming in.
Yeah. It's not technology, it's mindset. So you are selling your own tools. It may sound real, but you are selling your own tools. So that's the point, right?
One thing that I'll say in the answer to that question is that, I mean, look at the panel here. And the different vendors coming together. You will not see that in any other vertical or use case that we work. I think interoperability, open source, usage across different kinds of hybrid platforms, that is something that is top of mind for us. And that's the kind of platform that we are trying to build on top of the cloud. It will take a while, but I think that's the end goal that we are all working towards.
Right. And that's why, when I was showing the slides, we have, we are growing our cloud presence. However, we are also doing something called interconnect with other cloud vendor. So that way, if that cloud vendor has some niche tool, they are best in doing that, let's use them. And let's use other cloud vendor what are best for them to offer, right? So those things are coming, as he rightly said. A lot of hybrid cloud is coming, and it is bound to come. There is no single vendor cloud system will be there down the road.
Right. So I have been with OSG forever, which has been in principle doing that since, I don't know, 20 years now. So it's not new. I'm just saying a lot of resource providers don't have that mindset. That's all I'm saying. I'm not saying it's not coming, it's not possible, nobody is doing it. I'm just trying to provide awareness.
So I'm going to take the risk of getting things thrown at me. And while I know I'm supposed to stand here as a good corporate citizen and say, yeah, and we do. I call the rest of them, we do some of the work around interoperability. So I've been doing this for a while at a couple of different companies. I was part of a company called Cycle where we worked with all 3 cloud vendors. Okay. Do you know how important that question was? On every single customer wanted to make sure that we provided multi-cloud support. Do you know how many people used it? 0. Okay. And I will say that over and over again. So when you talk about hybrid support, and I think he brought up a really good point, what you really want is the ability to move my data from one to the other. Because the truth is he's going to develop some technologies that are really good at this. And you're going to do some things that are really good at that. And what you want to be able to is not run the same job in all places, because that's ridiculous. What you really want to be able to do when you're thinking about hybrid is, how do I get my data from place to place so I can take advantage of all their strengths? And that gets lost sometime in this discussion. All right. So that's why I'm jumping on you a little bit, because you talked about, yes, you're going to have to write different scripts, but it's because you're doing different parts of your process. You're going to do that anyway. All right, I didn't get anything thrown at me.
So let me actually use that opportunity to thank you guys, because I tried to get multiple cloud vendors into the same conversation a few years ago and was told, if that guy shows up, I'm not showing up. So I actually want to really thank you. This is the first time that I have seen 4 cloud providers on the same panel. And that is a applause to you guys.
In all fairness, the applause goes to these people, because the Cloud Bank team came to all of us individually and said, look, this is kind of stupid.
Is that a,
Any other questions? I know, yep, oh, all right.
But yeah, we just but the reason why is because so another notion of the data is not able to move is because the cost models are pretty much the same. They're trying to trap the data within the ecosystem, right? And so again, we talk about a lot of different vendors and all of this, but the ecosystem monetize the data. So therefore it does make this very hard, right? This notion that we're going to share and this and that. And so I mean, I guess what I'd say is I push it back on the cloud providers. There's this notion that like, oh, this cost model is really cool and it's all whatever. It looks very, very similar. And so the notion that you'd have a different cost model that would, you know, cause upfront costs, again, just different costs. I mean, I've talked to cloud vendors about, hey, I want to keep my data for exactly 10 years. Can I give you money now? Okay, I'll give you money right now. And then we'll be done. And you promised me my data's there for 10 years. And at 10 years, which you guys all worry about, I want it to vaporize. I want it to go away. It's gone. That was the commitment I made.
I'll speak for me, but I'm going to bet that everybody else will tell you, right? We're all having this conversation with our bosses.
right. I mean, I think we do have to remember that these people are in here to make a profit, right? I mean, and right. Let's see. Yeah, no, I mean, I think what I learned recently, which surprised me, is that sometimes it costs money to move your data around within a cloud provider, like just to different types of platforms. So anyway, yes, it's a big problem.
Most of us, though, and I'm not pot, right? Do you have... All right, so we all have an egress waiver for these institutions. And the egress waiver is basically designed to say, hey, if you're an educational institution, it's a function of how much you spend and all that. I don't think anyone's ever had to pay for data egress because it always falls under the limit.
Yeah.
See? Oh, well, you're Los Alamos, man. You've got billions. You said you were trying to give us cash. Come on. Oh, man.
All right, I think we will wrap up, and I very much want to thank Google, AWS, IBM, and Oracle for participating. Really appreciate you coming out, and thank you so much for everybody listening and asking questions. And yeah, okay, all right. Oh yeah, okay, perfect. Thank you.
See, look at that, man. All the vendors. That was really fun. Thank you very much, as always.